Welcome everyone. In this video we are going to derive the rocket equation. So the equation that we're going to derive will help us analyze the motion of rockets. And let's get directly started. Let's draw ourselves a rocket, and I'm going to draw it as simple as possible. Let's imagine it is a rectangle like this. And this is the picture of our rocket at time t. Our rocket has a mass of m, and it is moving in one direction with a velocity of v. Now, if we fast forward a little bit, now we will be at another point. We will be at, let me draw the rocket first. We will be at t plus delta t, so a little amount of time passed. This is what delta means here. And our rocket will be moving in the same direction, let's say, with a velocity, its initial velocity, plus there will be a change in its velocity, so delta v. So we have its initial velocity and the change that occurred to it. And this is our rocket's final velocity. And since our rocket needs to propel itself in outer space, it also is pushing out gas. It is burning fuel. And imagine that this is the mass of fuel that was pushed from the back of our rocket. And this is going to be moving in the opposite direction to our rocket with a velocity of u. It is in the opposite direction, and this is a relative velocity. The fuel is coming out of our rocket at a speed of u, and it is in a negative direction, but this is a relative speed, and we will actually need to find the speed of this fuel with respect to an outer observer, and we will do that in a minute. And now the mass of our rocket decreased because it burned some fuel, and the mass is now the initial mass plus some change in mass. Well, where did this change of mass go? I mean, it can't just disappear. You guessed it right, it is the mass of our fuel. And I'm going to put a negative sign here. This doesn't mean that the fuel has a negative mass. It is just that delta m is a negative value. And it makes sense because we have m plus delta m. Our rocket burned some fuel, so its mass should have decreased. This means that delta m is a negative value. Now, to find an equation to analyze the motion of our rocket, I will consider the momentum at each time. So let's write the momentum for time t. And momentum, to symbolize it, we use p. So pt, momentum at time t, it is going to be by definition mass times the velocity of our rocket. So we have mass times the velocity. And now we will write the momentum at time t plus delta t. And you might be tempted to say, hey, momentum will be conserved. They will be equal to each other, but it might not be the case. That is not necessarily correct. There might be an external force. For example, there might be a gravitational pull from a nearby planet, okay? So at the end, we will account for that actually. You will see an external force term at our final equation, so stay tuned for that. And we need to actually represent this velocity before moving on. So let's do it. As I said, this is a relative velocity. This is relative to our rocket. So if we have, in general, velocity of A with respect to B, this is going to be equal to velocity of A minus velocity of B. And you can convince yourself that this equation is correct by considering two cars moving towards each other, moving in the same direction. I think that you can understand and intuitively get a grasp of this equation. So VAB in this case is negative u, and we are trying to find VA, the actual velocity of our fuel with respect to an outside observer, minus the velocity of our rocket. It is going to be V minus, don't forget the delta V as well. So I distribute a negative sign, which turns out that VA, the velocity of our fuel, is going to be equal to V plus delta V minus U. Alright, so we got that out of the way. Now we are ready to write the momentum at t plus delta t. this momentum is going to be equal to? Well, we can add the momentum of two objects separately. So we will calculate the momentum of our rocket first. What is its momentum? Well, its momentum is m plus delta m. This is its mass at time t plus delta t. Then multiply with its velocity, which is v plus delta v. Alright, and I want to separate this part. Let's not confuse it. So, cool. And now I'm going to add the velocity, the momentum of our field. Because remember, we are interested in the momentum of the whole system, consisting of the rocket and the field. And if we do that, we're going to have its mass, which is negative delta m. So let's even write the negative like this, delta m, times its velocity, which we just found here. So I'm going to substitute that. We have v plus delta v minus u. And that looks like a v, excuse me. Okay, cool. Now let's just distribute the parentheses and let's see what we get. We're going to have multiplying m and v. Actually, you know what? Let me multiply it quickly and then you can check that the multiplication is correct. So we're going to have mv plus m delta v plus delta mv, and then let's look like a v, a u, plus delta m delta v. This was the momentum of our rocket at time t plus delta t. Now comes the momentum of the field. We will have negative delta m v minus delta m delta v. That looks like a u, I'm sorry. And then a plus. You remember, negative gives you a positive. We have plus delta m u this time. Cool. Now I want to find the change in momentum. So what is delta p? Let's emphasize. Let's emphasize it. It will be in red. And oh my friends, these momentums, they are vectors. We can put their arrows as well. So yeah, let's put them. So what is delta p? What is the change in momentum? Well, we're going to subtract this momentum value. We are going to subtract the initial from the final. So we're going to subtract. Let me write it actually. You know what? Let's not confuse. Let's write them. We're going to have p t delta t minus p t. So this is the subtraction that we make. Delta means final minus initial, and that is exactly what we did. So the only thing that is going to happen is this mv is going to cancel this mv, and the rest is going to stay there. So, I don't even need to write it perhaps. This is directly, all of this is going to be here. That is the change in momentum. Now, here comes the interesting part. What if I say, I am not content with only finding the change in momentum. I want to find the change in momentum divided by change in time. So I want to do delta p. Let's do it with blue. And this was here. I want to do delta p divided by delta t. And I am not content with only taking delta t as my divisor. No, I want to also take the limit as delta t approaches 0. Because this is a definition. What is this a definition of? Remember Newton's general second law? This is a definition for the net force. The time derivative of p is going to give you the net force, because this deltas become, since we take the limit, these become dp by dt, and this is by definition, by Newton's second law, equal to the F, the net force. And I'm going to use a subscript external, ext, to emphasize that this is a force that is external to the fuel rocket system. For example, this is not the thrust force that is being generated by our rocket. No, this is not that kind of a force. This is an external force. This is like the gravity of a planet. So this is one side of the equation, but what is the other side? The other side is going to come from this box right here. We're going to express it. And also, notice these cancel. Delta M, delta V, and this cancels because they are opposite, and also this and this cancel. It is going to take shorter than I expected it. So those cancelled, and now we're going to have we're going to have this part. M delta V divided by delta T as limit delta T approaches 0. So M is a constant, it will come out of the limit, and we're going to have delta V over delta T as limit delta T approaches 0. That is going to give us a differential. That's going to give us a derivative. That is going to be dV by dt. Plus, we're going to have delta M times U. Remember, U is a constant. Our fuel is coming out of the rocket with the same relative velocity all the time. So U comes out of the limit, and we have delta M divided by delta T as delta T approaches 0. So that is going to give us a differential value. We're going to have a derivative, and that derivative is dm dt. And my friends, this is the rocket equation. This is the general rocket equation, and in my next video I plan to solve this equation where F external is equal to 0. So where there is no external force applied from outside. And when we solve that equation, we will get interesting results. Anyways, I hope this video was helpful. If you have any questions, please write them in the comment section. I hope to see you in another video.